Students, in this problem, they're giving us a combustion reaction, which would be a typical way for a chemist to discover something about an unknown compound. And they say, okay, your unknown compound only contains carbon, hydrogen, and oxygen. They burn or combust a certain amount of that unknown compound. In my case, it was 9.612 milligrams. And it yields a certain mass of CO2 and water. The general format of any combustion reaction is some unknown compound, which in this case is a hydrocarbon, something that contains carbon, hydrogen, and possibly oxygen, but whose formula at this point we don't know. So I'm just going to write the formula CXHYOZ. We don't know at this point what the subscripts X, Y, and Z are, but we do need to write the unknown compound's formula in some way. So let's just put CXHYOZ. In a combustion reaction, you need some kind of a gas to support combustion. That's almost always oxygen, and you can go ahead and presume that for all of these problems in Chapter 3. There are other gases that do support combustion, but oxygen is by far the most common one. We always produce, when combusting a hydrocarbon, carbon dioxide and water. Let's list the masses that they give us. My red numbers are 9.612 milligrams of the unknown. They don't tell us anything about the mass of the oxygen that reacted along with it. They tell us 14.41 milligrams of carbon dioxide are produced and 3.93 milligrams of water are produced. When presented with a combustion reaction, notice that on the product side of the equation, the only place that carbon appears is in the carbon dioxide, and the only place that hydrogen appears is in the water. Oxygen, however, appears in both carbon dioxide and in water. So we can't, the easiest way to approach this is to first figure out the mass of carbon that was produced in the CO2. And since they tell us that we've got 14.41 milligrams of carbon dioxide, we can use the mass percent of carbon within carbon dioxide to find how much carbon was produced. If you find out the molar mass of carbon dioxide, you would add the atomic weight of oxygen times 2, so 16 plus another 16. Carbon's atomic weight is 12. That all adds up to 44. So for every 44 grams, or in this case it would be for every 44 milligrams of carbon dioxide, we have 12 milligrams of carbon. In other words, the mass percent of carbon within carbon dioxide is equal to the fraction 12 over 44. So if they tell us you've got 14.41 milligrams of carbon dioxide and you set up a mass percent problem, you can use that to find the number of milligrams of carbon. And in this case it works out to be 3.93 milligrams of carbon. We'll do something similar for the hydrogen found within water. They tell us from the problem we produced 3.93 milligrams of water, and by coincidence the number of milligrams of carbon within carbon dioxide happens to match the number of milligrams of water produced. That's just a coincidence, and it's probably not going to be the same case for your red numbers. We're now going to set up the mass percent ratio to find how many milligrams of hydrogen are in 3.93 milligrams of water. Water's molar mass would be found by taking oxygen's atomic weight, 16, plus 2 times hydrogen's atomic weight. So 16 plus 1 for one of the hydrogen atoms, plus another 1. That gives you 18 for for the molar mass of water. And of that 18 milligrams within water, 2 milligrams were contributed by the hydrogen. So 2 over 18 is a ratio that allows you to find the number of milligrams of hydrogen within water. So I'll take on my calculator 3.93 times the fraction 2 over 18, and it works out to be 0.473 or 437 milligrams of hydrogen. Okay. Because we know about the law of conservation of matter, which says that atoms can't be created or destroyed in a reaction, we know that the mass of carbon that we find on the product side of the equation should be equal to the mass of carbon found on the reactant side of the equation. And similarly, the mass of hydrogen that you find on the product side of the equation should match the mass of hydrogen that you had on the reactant side of the equation. The unknown compound has only 3 elements: carbon, hydrogen, and oxygen, and we know how many milligrams we have of that in total. Well, since we figured out how many milligrams of carbon were on the product side and how many milligrams of hydrogen were on the product side, and since the unknown is the only source of carbon and hydrogen on the reactant side, we can just subtract to get the mass of oxygen. So my red number was 9.612 milligrams of the unknown compound. We had figured out that there is 3.93 milligrams of carbon and 0.437 milligrams of hydrogen. All we're going to do is subtract. The element that we haven't accounted for yet is the oxygen. So if you subtract away the mass of the carbon and the mass of the hydrogen, and the unknown compound only has carbon, hydrogen, and oxygen, then the remaining mass, which for me works out to be 5.245 milligrams, must be attributed to the oxygen. From here, we've got a problem like what you've seen before in yesterday's WebAssign. We have certain numbers of grams, or in this case they gave us milligrams, of each of 3 elements. We figured out that there is 3.93 milligrams of carbon in the unknown. There's 0.437 milligrams of hydrogen, and after subtracting, we found out that there's 5.245 milligrams of oxygen in the unknown. You can probably guess where we're going to go next. We're going to convert grams into kilograms, or grams into moles. Since they gave us milligrams rather than grams, there's an easy metric conversion that you can do. Just divide by 1,000 to get the number of grams. So I'll start by taking 1,000 milligrams of carbon for every 1 gram of carbon. And then the atomic weight of carbon is 12. So 12 grams of carbon for every 1 mole of carbon. And if you follow the units, milligrams crosses out, grams crosses out, and you're left with moles. In my case, that works out to be 0.000328 moles of carbon. For the hydrogen, similar setup, 1,000 milligrams of hydrogen is equal to 1 gram of hydrogen. The atomic weight of hydrogen is 1.0. So for every 1 gram of hydrogen, you have 1 mole of hydrogen. And if you follow the units, the unit that you're left with is moles of hydrogen, which is what you want. In my case, that works out to be 0.000437 moles of hydrogen. For the oxygen, very similar setup. 1 gram is equal to 1,000 milligrams. The atomic weight of oxygen is 16. The unit that's left is moles, and in my case, that works out to be 0.000328 moles of oxygen. Next, we'll write a provisional formula with decimals as subscripts. That technically is not proper, but that's okay. It will get us to the empirical formula eventually. So provisionally, I'd say, okay, we've got some carbon, we've got some hydrogen, and we've got some oxygen in the unknown, and we're going to use the numbers of moles that we had calculated as the subscripts initially. Next, once you've got your provisional formula, look at those subscripts and find out which one is smallest. And we'll divide all of the subscripts by that. As you do that, after making that division, look for whole number ratios, but also be aware that you might find a ratio that isn't a whole number, but it ends in 0.5 or 0.33 or 0.66, or even fourths, 0.25 or 0.75. In this case, we're going to divide all of the subscripts by the smallest one that we see. There's a tie for smallest in this case. 0.00328 is smaller than 0.00437. Two of these are easy to spot. This works out to be 1. This works out to be 1. When you divide 0.000437 by 0.000328, you do not get a whole number. Instead, you get a number that's really close to 1.33. So in this case, we're looking for a ratio that's a third. So this is really 1.33 is the same as 4/3. So when writing a neatened up formula, you might say, okay, C1 H 4/3 O1. And that maintains the ratio of moles that you had calculated, but it's in recognizable fractions. Lastly, if you have an improper fraction in your formula, as we have here, 4/3 is an improper fraction, multiply the subscripts so that you get rid of the fraction. So if I multiply all of these subscripts by 3, it still maintains the molar ratio, but I get whole number subscripts now. The ratio of 1 to 4/3 to 1 is the same as the ratio of moles found in 3 to 4 to 3. This is your empirical formula for the compound. Next little bit, and that was most of the work there. But if we go back to the original problem, they give us one other thing. They say the molar mass of the compound is 176.1. And they want us to use that information to find the molecular formula. Okay, we've done problems like this as well. It's just that this problem kind of combines a bunch of stuff. Okay, let's find the empirical formula mass. So within C3H4O3, we've got 3 atoms of carbon, whose atomic weight is 12, 4 atoms of hydrogen, and 3 atoms of oxygen. When you add all that up, you get 88. That 88 is the empirical formula mass, not the molar mass, the empirical formula mass. To get the molecular formula, we'll take the molar mass divided by the empirical formula mass. And when you do that, this time you should definitely get a whole number, because that whole number will tell you what to multiply the subscripts by within the empirical formula to arrive at the molecular formula. The problem gave us 176.1 as the molar mass. We had found the empirical formula mass is equal to 88. You could probably eyeball this. That's going to equal 2. So that means double all of the subscripts within the empirical formula in order to arrive at the molecular formula. So if the empirical formula was C3H4O3, your molecular formula will be that same ratio of the elements, but doubled subscripts. So instead of C3, I'm going to write C6. And instead of H4, I'm going to write H8. And instead of writing O3, I'm going to write O6. And there we have it, the empirical and molecular formulas of the unknown compound.